breaking them into signal processing components, implementing the waveforms, as well as signal conditioning components such as your amplifiers, antennas, along with distribution between them so that you can share amplifiers, antennas, or reconfigure them based on mission needs. And then finally, a variety of software frameworks to enable portable applications. So to that end, we've identified different frameworks for the various mission areas that we intend to support. So to go into the specific standards that we selected, from a network-based perspective, we leveraged the Army's investment in Victory, the vehicular integration for C4ISR EW interoperability. So Victory establishes a network data bus on the platform and defines wireline interfaces in order to discover, monitor, and manage capabilities in a common way. So time and position being the most common examples. With the modular open RF architecture, we extended Victory, again, for RF systems, allowing or defining standardized ways to discover RF resources, such as antennas, amplifiers, as well as overlaying the resource management to share them across missions. From a hardware form factor perspective, we adopted the industry standard OpenVPX, but we overlaid some DoD-specific extensions. For example, in the pinouts or the profiles that we defined, we made extensive use of blind mate coax and optical connectors to minimize the number of connections on the front of the card to facilitate maintenance. And then also to maximize interoperability, minimizing the number or eliminating the number of user-defined pins so there's no variability in how the pinout is implemented from vendor to vendor. And then finally, from a software perspective, we've adopted a variety of frameworks. From an SDR perspective or software-defined radio perspective, we've adopted the Red Hawk framework, which is a free and open source software. From a comms perspective, we've leveraged the software communications architecture. And then from an avionics perspective, we've leveraged the future airborne capability environment out of NavAir PMA 209. So to show how it all comes together, the approach has been referred by some as the universal A-kit, where platforms come with one or more chassis built to the common backplane. Platform is already plumbed for management and control of resources over the network, as well as distribution of RF signals from the chassis to external mount points. In this case, when a PM fields a new capability, they no longer need to worry about a platform-specific A-kit. They can simply provide a B-kit or their mission equipment consisting of one or more cards that plugs in the common chassis, as well as amplifiers and antennas that bolt to standard mount points and take advantage of the existing cabling on the platform. So to maximize commonality in the ecosystem we're creating with this approach, we've collaborated with various partners within other government agencies as well as industry. So we've worked very closely with the Air Force Lifecycle Management Center on their Sensor Open System Architecture initiative. So at this point, all of the standards that we've defined within CMOS have been proposed to SOSA and are being included in their specifications. So that should provide commonality between the Air Force and the Army moving forward. Similarly, worked very closely with NavAir PMA 209 in order to align the backplane profiles we defined with their hardware open system technology or host standard, which should again allow us to procure the same single board computers in the future. In terms of Victory, not only have we adopted Victory, but the MORE extension, we are in the process of actually transitioning to the Victory Standard Support Office. So in the near future, MORE will be included in the official Victory specification release. All of the enhancements we've made to VITA standards, such as OpenVPX for the backplane, also leveraging VITA 49.2 for digital RF. Those changes have all been propagated back into the VITA standards body and are included in the spec updates that were released this year. Worked very closely with TARDEC, another RDEC within RDECOM, in order to take the chassis that we have here and integrate it on a Stryker platform in order to do final validation of the architecture and specifications. As with anything, security is foremost. If we can't get the system accredited, there's no point in defining the architecture. So since the beginning, we've been working with NSA to make sure that the approach we've taken is certifiable. And then finally, pulling in experts from academia in order to help us extend the specifications as appropriate, such as the OpenVPX and the VITA-49.2 specs. With that, folks have any questions?
So how do you put teeth in this? So Victory, I'm most familiar with Victory, but it's them aspirational, for example, like on JLTV, they weren't really requiring Victory compliance. How do you get to that point in future vehicle systems or in future vehicle upgrades?
Okay, so the question is, how do you put teeth in this? How do you really get traction moving forward? So we've been taking a two-pronged approach to do that. The first was obviously working with the acquisition community, getting them on board with this approach, and more so getting solicitations and performance specifications to refer to the standards and the appropriate sections of those standards. So to that end, we are seeing solicitations starting to be released that are requiring CMOS standards. And the other way we're dealing with it is also working with industry, trying to get product base to naturally materialize that's compliant with the architecture. So whether the acquisition community requires it or products start to appear, end goal is the same. You get products in the field compliant with the architecture. Any other questions? Okay, if you think of any afterwards, I'll be over there for the rest of the day. Thank you.
Thank you, everyone. The next presentation will be at 3:15.
I said no.